Awesome. So, hey guys, welcome to Beginner Track. This is workshop 6, and today we're going to be talking about machine learning libraries. If you haven't joined the Discord yet or the Facebook, there will be links throughout the slides, and there's a feedback form which we'd love for you to fill out so that we can consistently work on what you feel about the workshops. So the purpose of this workshop is to mostly talk about libraries, some popular libraries that we use in Python for machine learning. And then we're probably going to go on to a code demo and we're going to explore them in real life, how they're actually implemented. So if you have any questions all through the workshop, please don't hesitate to unmute yourself, interrupt me, or just drop it in chat. And yeah, let's get started. Okay, before we get started, we have an event coming up on the 23rd of February. So ACM AI will be hosting the AI in coronavirus event, where it'll be held in Dodd Hall room 170. And I believe it will be recorded as well. So it's from 6 to 7:30 p.m. And we understand that a lot of people who've been attending our track offerings, be it beginner track or advanced track, are sort of trying to get majorly from a pre-med background or a background in medicine, who are trying to understand, the implications of how artificial intelligence can be used in the entire COVID-19 sphere. And for that, we're hosting a panel where we'll have Professor Gu come and talk about his work with the UCLA Statistical Machine Learning Lab and how it's actually panning out and covering a lot of things spanning through medicine as well. So if you're into that, we definitely love to see you there. And I guess with that out of the way, we can get started. So let's talk about libraries. Okay, I understand that most of the people who've joined beginner track are from CS31 or CS32 or are doing one of those. So you might have an idea of what a library is, but I'll just recap quickly. So a library is a compilation of functions, data structures, routines, algorithms, which are readily available for use. So they're naturally, as you might see on the slide, they're indispensable to research and writing complex programs. So the idea of a library is that instead of writing the same code over and over again, instead of writing the common functions that we use over and over again, since most of the functions are not inbuilt into Python, we just import libraries instead of reinventing the wheel over and over again. So it prevents us from writing redundant code. And we use them in many cases. Okay, so there's text processing, there is graphics, there is data manipulation, there is data visualization, there is scientific computation. So that's the general idea of what a library is. It's primarily to stop us from there are certain commonly used functions which are inbuilt into Python. Then there are more specific functions that we use for very specific reasons, for very niche spheres, which might include the ones listed on the slide. So for those, we import libraries instead of writing the code over and over again. So today I'm going to be taking a look at about 5 to 6 of the most popular libraries, and then we're going to be delving deeper into 3 of them. The 3 of them being NumPy, Pandas, and Matplotlib, for which we'll also learn how to write code and explore some basic functions. So first of all, let's talk about NumPy. Now, NumPy is arguably the most popular library for large multi-dimensional array and matrix processing. So all through regression, we've talked about arrays, we've talked about matrices. And when we want to deal with them, when we want to deal with them numerically, when we need high-level math functions, we actually import NumPy, which helps us play around with arrays and matrices and many, many, many other multi-dimensional mathematical objects. They're also used for fundamental scientific computations. So we talk about linear algebra, Fourier transforms, random number capabilities. And the major idea of NumPy is to take mathematical objects and play with them numerically. And it's naturally not very easy to do that with just the functions that we have in Python. So we import NumPy. And as some of you might know, you might have heard of TensorFlow, which is definitely one of the most widely used and popular libraries. And even TensorFlow internally uses NumPy for the manipulation of tensors. So that's NumPy. I'll say it again. If anyone has any questions, please feel free to unmute or drop it in chat. I will be monitoring the chat as well. I don't see anything right now. Okay, moving on. Let's talk about pandas. So pandas is also something we're going to be exploring later today in the code section. And pandas is used for data manipulation and analysis. So throughout beginner track, when we've worked with data, we've tried to pre-process the data. And by pre-processing, I mean that before actually, before we actually play around and impose functions onto certain models or certain data sets, what we try to do is we pre-process them. So pre-processing might include something like data normalization, or we just play around with the data set in a way that it is optimized to be run through our functions. So for that, we use pandas, okay? And pandas is used for a variety of features. It has a bunch of features, but it mainly plays around with the data set. And pandas also has this feature called data frames. Now, data frames, while they might sound somewhat complicated, but in reality, they're just, think of them as tables, okay? With two-dimensional rows and columns with different sizes, which are potentially heterogeneous. So in short, it's just tabular data, and we call them data frames. And pandas provides us with a bunch of ways, a bunch of inbuilt functions, a bunch of interfaces that helps us deal with data frames, that is tabular data. And of course, the features include data reshaping, pivoting, merging, and joining. And yeah, we also handle missing data, alignment of data. But yeah, the general idea is that we look at data in a two-dimensional space, and pandas provides us with functions to deal with them. Moving on, we have Matplotlib. Just a second. Yeah, in chat. So of course, now we talk about data visualization. So Matplotlib is, again, a Python library for data visualization. Now, data visualization, as the name suggests, is visualizing different patterns within the data that we have. And Matplotlib is primarily 2D. So again, we talked about two-dimensional stuff previously. Now we're looking at 2D graphs, 2D plots. So these might be error charts, bar charts, or histograms, or very basic two-dimensional statistical models, which we can plot easily using Matplotlib. And Matplotlib has this interface called Pyplot. Okay, and Pyplot is, I would say, probably one of the most used interfaces within Matplotlib, but Pyplot basically helps Matplotlib act like MATLAB. And MATLAB is a language, again, which is used for a variety of numerical and mathematical computations for plotting. So Pyplot makes plotting easy. Now, when I make a plot, I can play around with the plot in a bunch of ways, right? So I can change the labels of a plot, or I can change the colors of the data points in the plot. So Pyplot allows me to mess with the formatting of the plots, so to speak. And yeah, Matplotlib provides us with a bunch of graphs and plots for data visualization. Like I mentioned, histograms, bar charts, error charts, and so on. So jumping on to Scikit-Learn. So we've used Scikit-Learn already in the due course of beginner track. And Scikit-Learn is, again, extremely popular. It's built for classical ML algorithms on top of NumPy and SciPy. Now, both of these, we've sort of talked about NumPy. SciPy is very similar. Instead of numerical calculations, which we do using NumPy, for scientific calculations, we use SciPy. So Scikit-Learn supports supervised and unsupervised learning algorithms. Now, I do believe we covered supervised and unsupervised learning algorithms. Supervised are those where we have labeled data sets, which we use to train the data, to train our model and to predict our accuracy. Whereas in unsupervised learning algorithms, we mostly provide a bunch of data points to the model. And we say, look, try figuring out patterns within this data. So supervised usually so we've mostly looked at supervised so far. Okay, we've looked at regression, and we've looked at KNN. So both of them, which is classification, so both of them fall into the supervised learning. Whereas in unsupervised learning, we come across k-means clustering, we come across dimensionality reduction, and so on, which we will be covering in advanced track. So Scikit-Learn provides us with a holistic library, a holistic bunch of functions where we can play around with all of these. So yeah, and it's used for data mining and data analysis. Data mining is looking for outliers within the data, trying to figuring out patterns within the data, and data analysis is plotting out those patterns that we mined. So Scikit-Learn is extremely essential for all of that. Jumping on to the last two, which is TensorFlow and Pytorch. So let's talk TensorFlow. Now, I believe we all know what tensors are. Tensors are simply mathematical objects in n dimensions. So there are orders. Okay, think about scalars and vectors and try generalizing them. So there are scalars, vectors, and matrices. So scalars have they have 0 indices, whereas vectors have 1 index. Matrices have 2 indices. Try generalizing them and thinking of them as tensors. So with n indices, we're not talking about 0 order, first order, or second order, but n order of indices. We call that mathematical object a tensor. So TensorFlow helps us play with that. Like we've talked of before, TensorFlow actually uses Numpy for tensor manipulation internally, and it was developed by Google Brain. Again, as the name suggests, that's by Google. And yeah, it's an open source library, numerical computation. And yeah, we mainly run around with tensors. And as you might see, as we progress further into beginner or even advanced track, TensorFlow is essential for deep learning, right? We will be exploring deep learning in the future, but deep learning research, deep learning applications, playing around with tensors, all of that falls under TensorFlow. So TensorFlow, again, is widely used. I believe in a couple of the surveys that were conducted recently, TensorFlow is probably the single most popular library that is used for machine learning with Python. Now, hopping on to Pytorch. Pytorch is something that we'll actually be doing in detail in advanced track. We're looking at Pytorch. We have an entire workshop based on Pytorch. We'll be looking into this theoretically and writing code with Pytorch. But in short, it's an open source ML library built on Torch. Now, Torch was actually built for C with a wrapper in Lua, but that was adapted to Python. So we call it PyTorch. It's an implementation of Torch, so to speak. And it has an extensive choice of libraries. Again, this primarily runs around. This also has a sort of similar function as TensorFlow, although this also supports like computer vision, NLP. All of this also comes under TensorFlow to some extent, but PyTorch is one of the most competitive, one of the most widely used machine learning libraries. We talk about tensors with GPU acceleration, and yeah. So we've looked at 6 libraries so far, and those are the libraries we're going to be overviewing today. After this, we're going to be delving into a code section. So does anyone have any questions about libraries in general or the specific libraries that we looked at? All right, seeing none, I think we can delve into the code demo. So in the code demo, we're going to take a look at 3 libraries. We're going to look at NumPy, we're going to look at Pandas, and we're going to look at Matplotlib. So I recommend you check out this link, which I'm going to drop in chat right now. But yeah, I think I'll let Jensen take over for NumPy right now. Again, if you have any questions, I will be more than happy to take them. So please feel free to drop them in chat.
All right, can you guys see my screen? I'm going to take that as a yes. All right, so let's open the link. One sec. All right, so we prepare like a notebook for the coding session for this workshop. So first thing, please save a copy in Drive, because if you modify this version, it's not going to save. So please make a copy in your own Google Drive. I'll give you guys maybe like 20 seconds. All right, so like Naman mentioned earlier, NumPy is one of the most popular libraries in Python for ML and data science. And one of the reasons why it's so popular is because it's really simple, yet it's like really extremely powerful when it comes to like manipulating a large amount of data, which is pretty common for machine learning and data science application. So if you're thinking about like pursuing a career in data science or ML, it definitely pays to master NumPy, because a lot of the more sophisticated libraries like TensorFlow are also built on top of NumPy, and a lot of the operations are, I guess, interchangeable almost. And also like the API docs for NumPy is probably one of the cleanest for any libraries that I've worked with. So definitely recommend checking it out if you have like questions about really any of the things that we covered. So without further ado, let's first import NumPy as NP. And NP here is really just an alias for NumPy. So because NumPy is kind of long, so we don't really want to like type NumPy every time we want to like create like a NumPy array. So instead we can just use NP in the place of NumPy. All right, so the main data structure in NumPy is the NumPy array. So a NumPy array is really just an n-dimensional array type. It's also sometimes referred to as the ND array. And it's really just a collection of items of the same type. So you can think of a NumPy array as kind of like a equivalent of a list in Python, but it supports like a lot more functionalities that are useful for a machine learning application, for example. So let's begin by creating a NumPy array. So there are several ways that we can create an array in NumPy. So the simplest is probably by using the array function. So to create a NumPy array, we can pass in a Python list into the NP array function. So in this case, we have created a NumPy array of 3 elements, and we can actually print out the array. So it's just 1, 2, and 3. And the shape here is just 3 elements. So similarly, we can also create like a 2-dimensional array by passing in a nested list in Python. So note that this is a nested list because there are like 2 sets of square brackets here. So it's kind of like a list of lists in Python. And so when we print out the shape of our array here, we can see it has 2 rows and 3 columns. So this is what our 2D array represents. So to see this, you can also print out the array itself. So yeah, you can see how it has like 2 rows and 3 columns. All right, so we also like prepare like some exercise for you guys to make this a little bit more interactive. So this exercise is for you guys. So try to create a 1x3 NumPy array containing any values using what we covered so far. So namely the array function. So I'll give you guys maybe like 30 seconds to think about this, and then we can go through the solution together. If you have an answer, you can feel free to like type it in chat as well. Oh yeah, also for whoever just joined, this is the link to the collab. Let me put this in chat. Okay. All right, so let's go through the solution together. So I guess the first thing that you might be tempted to do is to create a Numpy array with 3 values like this. Let's also print out the shape. So as you can see, this is a 3x1 array. So in NumPy, usually if the last index is a 1, it just drops the last index. So the trick here is we want to create a nested list. So when we print this out, we have a 1x3 array instead of a 3x1 array. So yeah, you can think of this as like a row vector, whereas the one that we created was a column vector. All right. Okay, any questions so far? If not, let's cover some of the basic operations. So in NumPy, you can apply arithmetic operations to arrays element-wise. And as a result of applying the operation, we create a new array that basically contains whatever the results of the operation is. So let's create 2 arrays. So we have an array here, which contains these 4 values, and then our second array, which contains these 4 values. So first thing first, you can try to do addition. So the addition just operates basically element-wise. So we get 20 plus 1. So this is our first element in the result. And then 30 plus 2. So we get 32 as the second element, and so on. And subtraction also works the same way. So first element here is 20 minus 1, which is 19, and so on. Scalar multiplication also applies element-wise. So if we multiply each element in A by 5, then we get 100 as the first element, 150 as the second element, and so on. And I guess one more operations is the Boolean comparison. So this one is slightly different. It also applies element-wise. So here we're just comparing each element to the value 35. So here 20 is less than 35. So the first value here is true. And similarly, 30 is also less than 35. So the second value here is also true. And then the last 2 elements are greater than 35. So this comparison evaluates to false. So unlike in math and a lot of and many other matrix languages, the product operator, the star operator basically actually performs an element-wise multiplication. And if you actually want to compute the matrix product of 2 NumPy arrays, you want to use the @ operator. So let's go through a simple example. So we have created 2 matrices here. I believe these are both 2x2 matrices. So we perform an element-wise product. So A star B. So we get 2, 0, and 0, 4. And we can do a sanity check. So we get the first element by multiplying the top left element in A by the top left element in B. So 1 times 2 is 2. And then the top right elements we get by multiplying 1 with 0, so it's 0. And you can verify the last 2 elements are also can be obtained this way. So if you want to perform a matrix multiplication, you want to use the @ operator. So this is what we get if we multiply these two matrices together using the add operator. You can manually verify that this is indeed the results that you would get if you perform matrix multiplication. I'm not going to go over it right now, but yeah. So if you're using an older version of Python, you can also use numpy dot or numpy.matplotlib to multiply two matrices together. So this is kind of like a legacy thing. So you might see this in legacy code, but nowadays almost everyone uses this operator because it's like so much more concise. So a lot of unary operations like computing the sum of all the elements in the array are implemented as methods. So for example, if we want to sum up all the elements in B, we can call b.sum. So if you actually add up all these elements, you should get 9. And similarly, we can also compute the min and the max of an array by calling the min and max methods respectively. So by default, these unary operations apply to the array as though they're just a list of numbers. So regardless of its shape. However, sometimes we want to like only perform operations on a specific axis. So we can do so by specifying the axis parameter if we want to apply an operation along a specific axis of an array. So here we're going to go through like a 2D example of how this works. So first we create a 2x3 array containing these numbers. So if we just want to sum up all the elements, we can just call it array2.sum. And so this would give us a scalar. But sometimes we want to like sum up like each column. So to do so, we can specify the axis parameter as 0. So this would give us 5, 7, and 9, which is indeed what we get if we sum up this array by column. And the way to, I guess, visualize this is we're basically performing the sum along the axis that is specified. So since axis is 0, we're performing the sum vertically. So this would give us the sum of each column. And similarly, if we specify the axis to be 1, then we're effectively performing the sum along the first axis. So there's a row-wise sum. So I guess in this case, we're performing the min. So this is going to give us the minimum in each row. So I think the concept of performing an operation along an axis is sometimes a tricky concept in NumPy. So let me know if you guys have any questions on that. Obviously, this notion of performing an operations along an axis also applies to like higher dimension tensors. But I think if you understand this 2D example, I think you should be good to go. All right. If there's no questions, let's cover the next topic, which is universal functions. So NumPy actually has a lot of familiar math functions like min, cosine, and exponential. So in NumPy, these are what are called universal functions. And basically what these universal function does is they perform an element-wise operation on an array. And the result, I guess the return type would also be a NumPy array as well. So let's go through some of the most common ones together. So I think we can cover NumPy.exponential. So this basically just applies the exponential functions on each element in our array 2. And then similarly, square root just takes the square root of each element in the array. And sign also works comparably. All right. So one of the most useful thing that you can do in NumPy is, excuse me. So one of the most common things that you would do in NumPy is indexing, slicing, and iterating through an array. So the arrays in NumPy can be indexed, sliced, and iterated, much like list and any other Python like sequences. So let's go through an example together. So let's say we create this array, this 1D array here. And then, so to get the third element, we can use the square bracket notation to pass in the to index. So we run this, we do get the third element in our NumPy array. So this is an interesting exercise. So try to select the last 4 elements in the array that we just created and store them in an array called ex3. So the syntax is basically the same for slicing a list. So that's your hint. I'll give you guys maybe 30 seconds. And then we can go through the answer together. All right, so to select the last 4 elements, we use the square bracket notation again. So we can pass in -4, and then we can omit the last index because we're just getting the last 4 elements. So by omitting the second index, it's implicit that we're just going to go all the way to the end of the array. So this does give us 6, 7, 8, and 9. So that's the last 4 elements. You can also do something like the length of the array -4. So if the negative index is kind of non-intuitive, you can also do this, but it's less common because it's kind of verbose. And we also want to store this into a variable called ex3. All right, so that's our answers. So iterating through a NumPy array works the same way as you would iterate through a list in Python. So you can use a for loop to iterate through each element in our array. All right, so multi-dimensional arrays can have like 1 index per axis. And these indices are given by a tuple, which is separated by comma. So let's go through an example together. So let's create array 4. So our array 4 has the following shape. And then if we want to get like just 1 element in this array, we have to index into this 3 times. So we pass in like 0, 2, and 1 as the tuple. We get this element here, which is 9. if we pass in like fewer than 3 index, then we basically get a row. So we get this row if we only pass in 2 numbers as our index. And so just like slicing, just like how we would when we slice a 1D array in NumPy, we can also slice an ND array. And the syntax here is the same. So we use this colon syntax for one of the elements in our tuple. So we pass in this, we basically get the middle 2 elements in the 3rd row. So we get 9 and 10. And the way this works is we start off, actually, let me print this array out. Okay, so the starting index in our slice is inclusive, but the ending index is not. So the index 1 starts here, which is a 9. And then the 10 has index 2, and then the 11 has index 3. So the 11 is not included because the slicing, the ending index in the slice is not inclusive. So we get 9 and 10. So we can also omit the numbers when we slice through an array to get basically all the elements in that slice. So we pass like 0, 2, and then colon as the last index. You basically get the entire row. We can also do the same for any of the index in our, I guess, tuple. So notice in the first example here, we can actually leave out the colon at the end, and this would give us the same answer. But in the second example, we can't actually do that because it'll be ambiguous basically for NumPy because the index that we're omitting is not at the end. So yeah, when fewer indices are provided than the number of axes, the missing indices are considered to be complete slices. So that's just a better way to say what I just said. Okay, so iterating through like ND arrays in NumPy is done with respect to the first axis. So let's create another array here. So there's a 2D array with the following numbers. So if we iterate through our array, we're iterating through each row. So the first time in this for loop, we're printing out the first row. And then the second iteration, we're printing out the next row here. So yeah, that's one way to think about iterating through an ND array. And so if you want to perform like an operation on each element in the array, you can use the dot flat attributes in the ND array class. So if you print this out, array 6.flat basically flattens the array into 1D. And then if you iterate through each element in the flattened array, you get each element. All right. Any questions so far with respect to like indexing and slicing?
So how are we gonna use all these and like later like machine learning like applications and stuff?
So your question is, how are we going to use this?
Yeah, because like we're dealing with like a lot of like matrices and like matrix operations and those kind of stuff, right? So so we need like all these like functions, right? That's why like Python implemented them all.
Yeah, so these are some of the most common operations that you would perform on like data, which are usually stored in NumPy arrays. So I don't think So I don't think in our guided projects we're going to use like every single one of the things that we covered, but this is just like a good starting point. There are also like a lot more stuff that we can cover in this workshop, which is why we include the link for the NumPy API docs. But these are the stuff that would come in handy if you want to, like, I guess, pursue a career in data science or ML.
Yeah, yeah. Just like, yeah, I was just like curious, like, because we do deal like a lot with like matrices and all these stuff, and like I was just wondering how these are like applied like in actual like implementations and, you know,
Oh,
like,
okay,
learning
gotcha.
models.
So we're gonna actually go through like a few examples in our next two workshops when we worked on our guided project. So I guess by then it'll probably be more clear how this would be applied. But now we just want to like cover all the, I guess, foundational stuff that you would need to actually do those guided projects. All right. All right, so let's cover NumPy array, some of the attributes for our NumPy array. So the array class in NumPy is called the ND array class. So note that the NumPy array class is not the same as the standard Python library array.array class, which some of you guys might have experience with. So NumPy arrays are generally more powerful with more functionalities that are useful for ML. And some of the attributes, some of the most notable attributes of an ND array object are the following. So the first one is ndarray.ndim, which is the number of dimensions or axis of the array. So recall our array4 as a 3D tensor that looks something like this. So if we print out the number of dimensions, we get 3. So this is just the number of axes. And then the second attribute is related. It's called ndarray.shape. So this is actually the actual dimension of the array, and it's generally returned as a tuple. So array4 has the following shape, so 2, 3, 4. And so if you look at this array here, this should make sense. And the next attribute is ndarray.size. So this is just the total number of elements in our array. So we print out the size of our array4, we get 24. So you can get this by just multiplying all of these numbers in the shape together. And I guess the last attribute that is useful or that we want to cover, there are actually like a lot more useful attributes, but this is the last one that we're going to cover. So this is the data type of the NumPy array. So I think Naman said earlier that the data type of an ND array has to be homogeneous. So this attributes give you the data type of the ND array itself. So we print out the D type of our array. We get that it's a 64-bit integer. So yeah. But like, I guess there's like some more like diversity. Usually, if you create like a NumPy array, you might want to make it a float, just so it's easier to work with if you want to like compute the gradient for like gradient descent. So yeah, I guess you guys have any questions with regard to like attributes? Also, like, am I going too fast or too slow? Or just right?
I think just right.
Okay. All right, cool. All right, awesome. So one of the bread and butter things that you would do in NumPy is manipulating the shape of an array. So I guess the shape of an array is just given by the number of elements along each axis. So let's go through this example here. So array 1 has 3 rows and 4 columns. And so sometimes in machine learning, you want to change the shape of an array. And you can do so with a number of different commands. So I guess which command you want to use depends on the situation, but we're just going to cover like a few of the most common ones. And so note that all these commands actually do not mutate the original array. Instead, they will return like a modified array that's distinct from the original array. So the first one is just ravel, which basically flattens the array. So here our array is a 2D matrix, and by calling ravel, we return a 1D array. And if you want to verify, array 1 is still 2D. So we didn't actually change the original array. So the second command, I guess, is the reshape command. And then basically the way this works is you pass in some number of parameters. So 6 and 2 is just the new shape that we want to reshape array 1 into. So as you can see, the reshaped array now has 6 rows and 2 columns. And so something to note that here is that the new shape has to be, so the size of the array has to remain invariant. So this makes sense, because if you pass in like 6 and 3, this is not going to work, because basically you can't reshape the array of size 12 into 6 by 3, which makes sense. So yeah, another operation that is quite common is the transpose operation. So if you're not familiar with the transpose operation, you basically just flip a row into a column in your original array. So this is also quite common in machine learning. Sometimes you want to like transpose an array in order to make like, I guess, an equation work. And so something to note here is for the reshape operation is if one of the dimension is a -1, then its value is going to be automatically calculated by NumPy. So I think up here we reshape array 1 into 6 by 2. And so we can also reshape it into 6 by -1. And the -1 here is implicitly calculated as a 2, because it's the only number that would make this work, as we discussed earlier. All right. So yeah, there are other useful ways to create a NumPy array. So the motivation behind that is like sometimes like the elements of the array are unknown at the beginning, but then we know the size of the array we want. So I guess because this is so common, NumPy actually offers like several functions to create arrays with like initial placeholder content. So these basically minimize the necessity of like changing the size of the array, which is quite expensive because you have to like reallocate like a different chunk of memory in order to like increase the size of the array. So that's pretty expensive. So the first function here is np.zeros, which basically gives you an array of 0 given a particular shape here. So this basically returns an array of zeros of 10 rows and 2 columns. And similarly, numpy.ones also gives you an array of 1s. So these 0 like initializing your array as zeros or ones are probably one of the most common things that you would do. So that's why these two functions are implemented in NumPy already. So sometimes we might not even know if we want like an array of 0 or 1s. So the function empty basically just gives us like a bunch of garbage as the initial content. So if you run this like multiple times, I believe this should be, okay, never mind. So in theory, empty should give you an array whose content is initially random and depends on the state of the memory. So it's generally good practice to actually like write a for loop or something to initialize the content if in your array if you initialize it this way, because it's going to lead to undefined behavior if you don't. So yeah, any questions so far? If not, I'm gonna go over how to create like sequential data in NumPy next, which is also like a very common operation. So sometimes we want to like create like a sequence of numbers, and NumPy provides the arange function, which is analogous to the built-in function in Python range. But in this case, this returns a NumPy array instead of like a range object. So here's the syntax for np.arange. So we specify the start and stop index, where start is inclusive, where stop is not. So this is exactly how range works as well. So here the NumPy array starts from 0 and goes all the way to 10, but not including 10. So notice how the parentheses here is like a open parentheses. So it's like a open range. So optionally, we can also specify the step size in between each number. So we pass in an additional parameter, which is the parameter step. And note that step has a default value of 1, which is why the default increment here is 1 when we did not specify the step. So if we run this, we should get 10, 15, 20, and 25. And the step size here is indeed 5. And arange also accepts like a step size as like a floating point argument. So you can verify it by running this. And this is like sometimes useful. And notice how the data type here is now, I guess, a floating point. Let me actually check what this is. Okay, so it's float 64. So it's a 64-bit float. Okay, so there is something in chat. Okay, I don't think that's a question. Never mind. Okay, so the issue with arange is if we use it with like a floating point argument, then it's generally not possible to perfectly predict the number of elements in the result due to like the finite precision for floating point numbers. So for this reason, it's usually a better idea to use the function linspace, which receives as an argument the number of elements we want instead of the step size. So the syntax is almost identical, and like the third argument here is the num instead of the step. So num has a default value of 50, and it has to be non-negative. So we do np.linspace starting from 0, stopping at 9, or stopping at 2 with 9 numbers. So we get this sequence of number. So notice how 2 here is included. So for linspace, this is pretty confusing, but for linspace, the endpoint here is inclusive by default. So we can optionally exclude the endpoint of the interval by passing in an extra argument called endpoint. So if we run the same code again, but adding this new argument, we get like a slightly different sequence. So notice how the 2 is now not included as the last number. So yeah, here's a good exercise. So try to create like a sequence of 30 like evenly spaced values from 0 to 2 pi. So I'll leave it up to you to consider which function would be more helpful. So either a range or linspace. I'll give you guys maybe a minute to think about this. Also, if you guys have any questions, now would be a good time to ask. All right, so the solution for this exercise is to use linspace. And then we want the start to be 0. And then the end to be 2 times pi. And then I think we want 30 values. So pass in 30 here. So yeah, this is what we get. So hopefully that makes sense. So another thing that comes in handy, but might not be intuitive at the beginning, is to conditionally select elements with like Booleans. So we already covered how to index into Numpy arrays using arrays of integer indices. So in that case, we're just basically providing a list of indices for the array to pick from. So actually, I can do an example. Let's see. I guess, okay, what's the last thing that we defined? Array 1. So I believe we can actually index into array 1 by using another Numpy array. So, okay, this is kind of confusing because 2D, but let me flatten array 1 and then store this into maybe X. So I can index into X by using another Numpy array. So let's say I want to get the first element and then the 6th element. Okay, that's in print. Okay, so yeah, this gives me the first element, which is a 1, and then the 6th element, which is a 6. So we can also use a similar notion by using Boolean indices, but the approach is slightly different. So in this case, we explicitly choose like which items we want and which ones we don't. And the most natural way to think about like how Boolean indexing works is to use Boolean arrays that have the same shape as the original array. So let's go through like a simple example here. So let's just create like a 2D matrix with the following values. And then here we just want to choose the elements that are greater or equal to 50, which is where this Boolean comparison comes into play. So array 7 res is a Boolean array of the same shape as array 7. So now we can use the notion of Boolean indexing to select all the elements in our array 7 that are greater or equal to 50. So this is what we get. So yeah, I guess the next exercise here is to select all the elements in array 7 that are divisible by 20 and then store them in ex4. I'll give you guys like another minute to think about this, and then we can go through a solution together. All right, so the trick for this exercise is to figure out like how to express the notion of, I guess, divisible by 20. So to do that, we can do array 7 mod 20 is equal to 0. So we do this, we get an array of Booleans. So we can store this in like a temporary variable. And then we can use this Boolean array to index back to our original array. So we get 20, 60, and 40. So these are indeed divisible by 20. And then we want to store them into a variable. All right, so this is the answer for the exercise. So recall in our last workshop, we went over the softmax function in multi-class classification. So this is actually a really good exercise to for you guys to, I guess, remember what you guys learned. So the exercise here is to implement softmax, which we have provided the equation to here. So yeah, I'll give you guys maybe like a couple of minutes to think about it. Mark, do you have a question?
Sorry, but for the solution of the previous question, I didn't quite get it. So, okay, I get the first line, but so in the second line, so what exactly are you doing?
So I am using a Boolean array to perform this Boolean indexing operation.
Yeah.
So we're here, I'm just picking like which elements I want to include.
Okay.
So I can print out temp again. So you can think of this as like a mask, basically. So let me print out array 7 as well. So here I'm just applying this Boolean mask to this array. So for 70, so since we have false here, so this does not appear in the final result. And then for this element, it's 20, and the mask here is true, so we do include it. And you can basically apply a similar notion for all the other elements. And the thing to note here is the final result here is always going to be 1D, even though we're starting off with like a 2D Numpy array. So if you want the final result to have like some dimensionality, you want to like use the reshaping operations that we discussed earlier. Okay, does that make sense?
So that's like a special functionality, right? So if you put in like Boolean values for array indices, if it's false, it's not displayed. If it's true, it's displayed.
Yes.
Okay. And also, like you said, like you have to convert it back to one-dimensional array.
No, it's just done by default in NumPy.
Oh, okay. Yeah.
So if I print out like ex4, not shape. So there's like a 1D array with 3 elements. All right. Oh, you guys like another minute to implement softmax. And I do believe the values here are correct. So if you implement this correctly, you should be able to get the same values. Obviously with like the rounding error, but it should be quite similar. All right, since we're running a little bit short on time, let's go through a solution now. So the first thing here is to exponentiate our input array. So I'll call this exp array equals. So we want to use the universal function np.exp. And then the next thing here is to divide our exponentiated array by the sum of that array. So return exponentiated array divided by exponentiated array dot sum. So recall sum is one of the methods for our ND array class. So if we run this, we should get values that are pretty close to the one we have up here. I guess obviously there's rounding error, but yeah, hopefully that makes sense. So do you guys want like a break? Or can we just carry on to the next section? I'm also gonna pass it to Claire right now. Sorry, do you have a question?
No.
Okay.
Can you see my screen?
Yeah, you're good to go.
All right. So I guess I'll start then. I'll be covering Pandas and Matplotlib, the other two Python libraries that you guys might see in the guided project later in the quarter. So we'll start off with Pandas. As Naman said before, Pandas is really good in handling data and displaying data and cleaning data. So they have their own way of storing data. So we'll show you how to do that now. Now, as always, we'll start with importing Pandas, and we're also importing NumPy because it's that commonly used. Let's see if it will. There you go. So here's a visualization for you of how Pandas stores data. This might seem familiar to you. It looks kind of like Excel or Google Sheets. because it's a very similar style. You have your rows and your columns, and Pandas calls it a data frame. So how do you create a data frame? Well, we can use the data frame function within Pandas to create a data frame from the data we have here. In our case, we have a bunch of dictionaries. So if we run this really quick, then we'll see it printed out nicely like this, where we have our rows and our columns. The columns are the individual headers, and then the rows are each value within those, I guess, titles. So now that we have our main data frame, now how do we use it? Well, usually when we want to access our data frame, we want to get to our columns or our rows. So we'll show you how to do that right now. To get the columns of a data frame, you can just call the name of the column with square brackets, like it would be for an index, to your data frame. So in our case, we have A as our column name. So if I run this right here, then we get all of the values that have A attached to it. As you can see, it will also print out the name of the column as well as what type of data is within the column. Now, for the column itself, if we run the type of the column, we'll notice that it's actually a series. And so what a series is it's a one-dimensional ND array, as you remember is NumPy, with axis labels, or in our case, A. So similarly, quite similar to NumPy, if we want to extract multiple columns, we'll just pass in, not exactly a tuple, but we can pass in multiple at once through this kind of format. So if we want our columns A and B, then we pass it in through an array kind of structure like this. And if we run this, then it will just print the values of the columns of A and B. To get the rows of the data frame is slightly different. There's a function for that called iloc. So now we will just pass in the row index in order to select what row we want. So in this case, we have the first row, which is the index 0. So if I run this, then we see the values of everything in the first row, which if we remember was 1, 2, 3, and 4. Now, the type of our row is also a series, aka a single dimensional array with an axis title. If we want to slice some arrays, this is very similar to a Python list, or as Jensen just covered, a Numpy array. So if we run this, then we also have our first 2 rows. Remember that the last index is not inclusive. Now, one of the best things about Pandas is you can access CSVs, which is used to store data. I believe you can also use JSON. But basically, you can take a bunch of data and then organize it so that it's ready for you to use in your model. So in this case, we have some data from online, and we can read it using Pandas Read Csv function. So we run this really quickly, and it will show you what kind of data it contains. It can seemingly contain a comparison of someone's SAT score with their GPA. And you can see right here it has 84 rows and 2 columns. So to clean our data, in this case, we don't have any missing values, but sometimes you will have some missing values in the data set. So there's a function for that within Pandas called isNA. And if we run that really quick, it seems that there are some with missing values.
Actually, there is none because they're all false.
Oh, I see. Okay.
So that means there's
Cool.
no missing values.
I was right to begin with. So there's no missing values. So as you can see, this returns an array, as Jensen showed us earlier with that example, of Boolean values. So in order to detect if any of these are true, then we can just run this function with any, which will tell us if any of them were true. And we don't. So let's say we have some data that we have right here with some missing values. And if we run this right here, then it will show with NumPy not available that we have several missing values right here. Now, if we were training a model, sometimes we wouldn't really want this to be displayed as a missing value, but we can just fill it with 0. So this function, fill NA, if it's missing, then it will just fill it with 0, which will be very helpful to us when we're training our models. So as you can see, when we run this function, all of our not available are filled with 0. Does anyone have any questions on Pandas so far before I jump into Matplotlib? This should be most of the functions that you would need for a guided project, but these are like the basic ones that are most common anyway. Okay, then I will continue on to Matplotlib. Again, this is quite a basic overview, so I'll be covering just a couple of the most common functionalities, but you'll see these in your guided projects, so I hope that this helps. So first of all, we're going to download Matplotlib Pipeline. Oh, this is commented. And we're going to jump right into some certain types of graphs that you might be used to. So if we want to graph a continuous function, such as x squared, a sine of x, x plus 4, then we would use something like matplot plot function. So right here, I'm using NumPy's sine function, which is a universal function, I believe, and I'm just generating a whole bunch of points. And I labeled the graph for convenience, just to make it a little bit more readable. But right here is where we plot it. So if I run this with my x and my y, you can see that it'll display quite nicely with the x and y values. So you can, as long as you have your x and y as a function you want, then you'll be able to create a continuous graph like this. So on to the next one, we're going to try a scatter plot. So I've imported a module from NumPy called random, which I'm going to use to generate a bunch of random integers. So if you were to run this, then yours is going to look a little different than mine because these are being randomly generated. And again, I've added some titles and some labels to make it look pretty. So if I run this, you can see that I just get a bunch of dots scattered around the graph. Now, if you want to change the appearance of your graph, then you can use the variables marker and color. So marker is something like an X, maybe a plus, and then I can change this to blue. And if I run it again, then we have a bunch of blue pluses. Now, the last one is slightly less common, but you might come across it. So I decided to throw it in here just in case. It's a bar chart. So let's say we have a certain number of categories and we know how many values each of these categories contain. So we would use arrays like this to indicate that. And again, I've added some titles, but the bar function is what will let us display this as a bar chart. So if I run this one, now we get a nice bar chart. So to recap, we've covered some continuous functions, in our case, sine, and then we have a scatter plot with just a scatter function. And then if you want a bar chart, then just use the bar function. So this is just the beginning. Matplotlib has quite a bit of implementation in it, and their docs are fairly readable. So if you want to know more, I've linked in the documentation to each of these functions, as well as the overall Matplotlib documentation. So there are some cool examples on there if you want to check it out on your own time. But for now, that's the end of the workshop. Thank you guys so much for coming. Next week, we'll be started on the guided project. And if you have some time, please look at the feedback form, fill it out. And we have the Facebook link here as well. Thank you so much.
Thank you.